All right. Good afternoon and good evening, everyone. So welcome back to the live interactive session of the course Viscous Fluid Flow. So today is actually a pre-poned class. So basically, there won't be any class tomorrow. The lecture or the session from 3 to 5, which was earlier scheduled to happen tomorrow, that is on Saturday, is pre-poned today from 7 to 9. So however, this is just for this session only, and all other sessions, the timings will be the usual timing, that is on Saturdays from 3 to 5. So with this, let us begin this week's session by recapitulating what we learned in the previous week. Uh, so let's have a quick recap of what we did in the previous week. So we began by solving the fluid flow problem of a belt which was moving in the plus x direction with some velocity u naught, and as the belt moves it drags the fluid along it, and because of this there is a balance between the gravitational force which acts on the fluid in the negative x direction and the viscous force basically which actually acts in the positive x direction, and so there is a balance between these two forces. And because of this balance, what we basically did is we found out what will be the velocity profile, keeping in mind the certain assumption that the flow is fully developed, which we again said is attributed to the fact that the belt is infinitely long and we are neglecting the beginning and the end effects of the belt. So the idea is that we consider the belt to be infinitely long, and we are just looking at the middle portion here, which is basically the fully developed assumption. And then we again looked at the steady flow problem, and of course the fluid was Newtonian and the flow to be one dimensional. So what we did is we solved the continuity and the Navier-Stokes equation. Again, as we have seen repeatedly, the continuity equation suggested that for a 1D flow, the x direction velocity is just a function of y only, and this basically simplified the x momentum equation as well. And what we did is we found out that the velocity profile was basically something like this. So keeping in mind that the boundary conditions at the surface of the belt is the belt velocity itself, and when you move far away from the belt, uh, the fluid velocity diminishes to zero, which are basically used to evaluate the constants C1 and C2. And then we got the velocity profile. The second problem, which was basically a numerical problem, was on the fact that there is a fully developed flow in a plane, in a pipe, which is generally termed as the Hagen possible flow, with a pressure gradient. However, its magnitude was unknown at that time. In contrast, it was given that the diameter of the pipe is known to us, the mass flow rate, and the corresponding temperature was also known. So with this, what we were asked to find out is the maximum velocity of the water that is flowing through the pipe, and the pressure gradient is basically driving the flow. So the idea of solving this problem is that we know that for this Hagen possible flow, the velocity profile is indeed a parabolic profile, which is basically of this form, as we all know. And the fact that the maximum velocity is basically the velocity when the radius is zero, basically is the center line velocity if we keep the axis at the center line of the pipe, as you can see from here. So with this, we found out uh, the maximum velocity, which is of this form. However, we saw that the mass flow rate is always associated with the average velocity. So we need to find out the average velocity from the maximum velocity. And we know that for a pipe flow, the average velocity is half the maximum velocity. This enabled us to find out V average. And once V average is known, the V maximum is basically 2 times the V average. So the V average, as you can see, is calculated from the mass flow rate because it was known to us and the cross-sectional area was provided to us. And once V average is known, using the expression for Vmax, and once Vmax is also known from V average, we found out the unknown pressure gradient that was initially driving the flow. I mean, that was essentially driving the flow. So this was the idea of the second problem. The third problem was a little, it was a little extended problem, and it was a little long. However, this involved the fact that in this problem, there was two cylinders, so this problem was known as the excursion problem, where there was two cylinders which were basically rotating with angular velocities omega 1 and omega 2, where omega 1 and omega 2 are the angular velocities of the smaller and the bigger cylinder, bearing radius A and B. And in addition to this rotational motion, there was also a axial pressure gradient that was applied, which is obviously known to be, let's say, dp/dz. And we said that this dp/dz was numerically equal to g. And based on this fact, we were asked to find out the velocity profile for this problem. So this was essentially the problem that we solved. The important bit of this problem is that in all the earlier problems that we solved, for instance, the pipe flow problem or all the earlier problems that we saw, it was essentially an 1D problem where there exists only one component of velocity, let's say the x direction velocity. In contrast to the earlier problem, what we saw is that this problem is not essentially a 1D problem, because it involves the rotational motion, due to which we can see there would be a velocity in the theta direction if we follow the cylindrical coordinate system. And in addition to this theta direction velocity, the axial pressure gradient will also drive a flow in the axial direction, because of which we will see two velocity components, uz, which is due to the axial pressure gradient, and u theta, which is basically due to the rotation of the cylinder. So this mandates the fact that this problem is two-dimensional in nature. And however, using certain assumption that the flow is axisymmetric, and we saw the meaning of axisymmetry in cylindrical coordinate system in the last class. We assume the flow to be fully developed, and using these assumptions, of course, it's a steady flow problem. We saw that we could identically, or we could at least analytically find out the velocity profile in both the directions, in the theta and the z direction, by using the momentum equation in the theta and z direction. In theta direction, we saw that the simplified Navier-Stokes equation in the theta direction essentially the simplified Navier-Stokes equation in the theta direction essentially boils down to a equidimensional equation which we followed a certain technique to solve it. So this was basically the equidimensional equation. The reason behind why this is known as an equidimensional equation is that the dimension of all these terms, this r square d2u by dr square, and this r d2u theta by dr, and all these terms, dr is the same dimension of this u theta, and that's why this is known as an equidimensional problem. And the solution technique was that we assume u theta to be of the form r power k, and our job was to eventually find out what would be the value of k. And from that, using the boundary conditions on the cylinder surfaces, we found out what will be the theta direction velocity, which basically appeared something like this. Thereafter, what we did is, as you can see, this u theta is indeed just a function of r. So we are just solving ODEs here, even if it's a two-dimensional problem, which is again based on the assumptions that we considered. However, since there was a z directional velocity as well, which basically mandates the fact that now we'll also get a uz direction velocity. This means that there will also be a flow in the z direction, and we use the Navier-Stokes equation in the corresponding z direction to find out what will be the value of uz. And again, integrating it, we saw that uz is basically of this form, and using the fact that there would be no slip on the cylinder surfaces, and on the cylinder surface, the flow would just be in the theta direction, owing to the no slip boundary condition, we found out the constants b1 and b2, which are required in evaluating the z component velocity. And of course, if we plug in this b1 and b2 in this z direction velocity that we saw, this would give us the two velocity fields u theta and uz by separately solving the Navier-Stokes equation in the theta and z direction. So this was something that we did in the last class. However, I said that in this week, before starting anything new, we would recapitulate basically what we learned. So we indeed recapitulated what we learned in the previous week, and as an extension of our analysis, in this week we will see certain special cases of some of the results that we got in that exclusion problem, and we will try to analyze like how these special cases physically mean in the context of the problem that we that we solve. So yeah, so this was the agenda. So yeah, so I was just recapitulating what we did in the last class. So there's nothing new that I started. So I would again wait here for some more time. So again, the agenda for this class is to see certain special cases of the last week's problem. And these special cases will obviously help us in getting further insights of this problem. And we will see like certain physics also evolve out that how the balance of forces basically takes place in such kind of problem is something that we are going to see today. And once that this thing is done, we will start something new today. And this is little bit off track of some of the lecture series that we have learned till now. Nevertheless, this idea is basically important to us in every fluid mechanics problem. So the idea is understanding what is non-dimensionalization and scaling analysis in the context of fluid mechanics. I mean, in the context of solving fluid mechanics problem. So we will see basically how to non-dimensionalize a problem. And in order to non-dimensionalize a problem, we need to know certain things, which is known as the scaling analysis and the order of magnitude that prevail while we use the scaling analysis. So these are the two things that we are going to see today. And in the next week, we will solve a problem which is associated with the lecture series of this week and the next week. And in that problem, we will solve that problem non-dimensionally. And we will see like how non-dimensional and scaling analysis indeed help us in getting results quickly. So this is the idea. So we will go through this very slowly. You don't need to worry about it. But we'll start off with deriving a special case of the last week exclusion problem, as I have already said. And let's see what do we get from that. But starting, before starting this week, I would again stop here for some time, maybe some couple of minutes. If you have any doubts related to the previous week's class or something that is related to the older classes as well, you can bring it here, or you can of course see the recording that is done here, and then you can post it in the discussion forum of the group. Uh, so I'll wait here for a couple of minutes, and then we will start the session for this this week. Meanwhile, I'll just check the recording is done. Okay, so it's done. All right. So I'll wait here for 2-3 minutes. You can revisit your notes if you want to see what was done in the last week. So as I have again said, so so we will start off by deriving certain spatial cases of the velocity profile u theta that we got in the previous week. Uh, and these spatial cases indeed, as we will see, it is indeed gives us certain physical insights of the problem, as we will see shortly. All right, so let's begin. I hope you don't have any doubts till now. So let's begin by understanding the fact that, so what did we do basically in the last week's problem? So there was an axial pressure gradient, as I have said, and the two cylinders was basically rotating with velocities omega2 and omega1, where these omegas are the angular velocity, as you can see, bearing the magnitude of radian per second. And the radiuses of these two cylinders were A and B. And the fluid was basically inside, it was basically in the concentric area of these two cylinders. And in order to drive the fluid axially, there was an applied pressure gradient. And what we did is we solved the velocity profile u theta and uz by simultaneously or like by like solving the theta direction Navier-Stokes equation and the z direction Navier-Stokes equation. So now, and of course, the velocity profile that we got in, let's say, in the u theta direction is basically this. This is something that we did. So this is the big velocity profile that we got in the theta direction, of course, by solving the NS equation in the theta direction. So now let's start off with a special case. Okay, let's start off with a special case, considering the fact that the two cylinders rotate with the same angular velocity. Now that the angular velocity of the inner cylinder is exactly equal to the angular velocity of the outer cylinder, which means omega1 is basically equals to omega2, And let's say this is equal to some omega, which is basically known to us. Okay. And also, without losing any generality and for simplicity in understanding, let us consider that the dp dz is basically 0, which means that I have stopped the axial pressure gradient, and this means now the flow field will just be a one-dimensional flow field bearing only the theta direction velocity, and uz will basically be equals to 0. So this is just for simplicity. This is just for simplicity, as we are dealing in special cases here. Okay. So let's do one thing. Let's invoke these two things. Of course, this means that this dp/dz will essentially now mean that uj is basically equals to 0 now. So we don't need to bother about what uj would be. Now we will only shift our focus in the theta direction velocity for getting certain insights. Okay, so what we will do is we'll invoke this omega 1 equal to omega 2 equal to omega in this theta direction velocity, and let's see what do we get. So if we put this, so the idea is if we put this in this expression, can you tell me what do we get? So just put omega 1 equal to omega 2 here in this expression. Can you quickly tell me what do we get? What will be the theta direction velocity? What will be?
Omega R.
Yes, exactly. So the theta direction velocity is just omega times r, as you have rightly pointed out. Okay. All right. So let's now do one thing. So yeah, so the theta direction velocity is omega r, and we'll just name it as equation 1. So let's now try to write something. So what we'll do is let us apply the Navier-Stokes equation in r direction now, and let's see what do we get. Because we already know that ur is 0, as I have already said, and as you guys also said that ur is 0 since these cylinders are rigid in nature. So the surface of these two cylinders are rigid. This means there won't be any penetration across the surface of the cylinder, which means ur essentially has to be equals to 0. Keeping this in mind, let's now apply the Navier-Stokes equation in the r direction, and let's see what do we get. And interestingly, we get a very important physics. We can actually get a very important result from this analysis. So let's systematically first write down the Navier-Stokes equation in the r direction, which basically is like this. That is rho times del ur. Just bear with me for some minutes. I will write down the r direction Navier-Stokes equation, and then we will see what we need to do. Okay. So the second term is ur times del ur by del r, plus the third term is u theta by r times of del ur by del theta, plus uz times del ur by del z. Okay, minus u theta square by r, which is equals to rho times gr minus del p by del r, plus, so what I am doing is I am just writing out the Navier-Stokes equation in the r direction in the cylindrical coordinate system, where the left hand side essentially denotes the inertia term, as you know. That's what I am doing. And this term becomes 1 by r, sorry, del r of 1 by r times of what? This becomes del r of r ur. Okay. This is done. Plus the next term is 1 upon r squared times, what do we get? So we get 1 upon r squared times del square ur by del theta squared minus 2 by r squared times del u theta by del theta plus del squared ur by del z squared. Okay, so this is just the Navier-Stokes equation in the r direction. Then let us now quickly invoke the assumptions that we saw in the last class. So there is no ur component of velocity, and of course it's a steady problem, which means this term is 0. There is no ur, so this term is essentially 0. U theta is of course non-zero, but ur is 0, so this term also boils down to be 0. It's a fully developed problem, so del ur by del z is equal to 0. And of course, since there is no ur, we assume, so we assume there is no body force in the radial direction, which means that this term essentially is also 0. Again, since ur is 0, you can just write this to be equals to 0. This is 0 because ur is again 0. And can you tell me what happens to this term? Can you tell me what happens to del u theta by del theta? Is it a 0 or a non-zero term? Can you tell me? So what happens to basically the term del u theta by del theta? It's a 0 or a non-zero term? So if you recapitulate, there was so we invoked an assumption which was basically the axisymmetric assumption. So the axisymmetric assumption in cylindrical coordinate means that if we just revolve around the z-axis, which is basically the theta direction, the quantities will basically remain the same. That means if this plane is the z-axis and we move around the z-axis, the quantities like u theta and ur and uz, this would basically be the same only, which means that any gradient in the theta direction will essentially turn out to be 0, and that's why this term del u theta by del theta is essentially 0. And of course, since ur is 0, this term also goes out to be equals to 0. So what we are left is basically something like this. So what we are left is, okay. So we will just end up in having non-zero terms this and the pressure gradient. Okay. So if we just write the non-zero terms, it will be rho times with a minus signs u theta, that is squared by r. Okay, and this is balanced by minus del p by del r. This is all that we get if we invoke the r direction momentum equation. If we invoke the assumptions in the r direction momentum equation, keeping in mind that we use the condition of axisymmetry, we use the condition of the fact that the flow is fully developed, and we use the fact that there is no r direction velocity, which is basically there is no flow across the surface of the cylinder. So if we do that, we get a balance between these two terms. Okay, and this cancels the minus term, which means that do you see something interesting here? So what we get is we get that del p by del r is rho u theta squared by r. And now if we, and as we know, u theta is basically omega times r. So u theta squared would basically be rho times omega squared r squared by r. Okay. Because u theta is omega r. So u theta squared would be just omega squared r squared by r. And so yeah, so if we just simplify this, this becomes what? This becomes this becomes del p by del r is equal to rho omega square r, or this can be written as rho r omega squared. Can you tell me what essentially is basic? So what this simplification of the r momentum equation is essentially portraying here? Can you tell me? Like, so what we saw is that, yeah, go on. Yeah, yeah, go on.
Centripetal force is balanced by pressure gradient.
Exactly. So that's what I really want to say. So and can you tell me what is the other name of this kind of motion? Can you tell me? That is true that the centripetal force is based, so the pressure gradient is basically balanced by the centripetal force. And what do we call this? Yeah, circular, or this is known as the rigid body motion. Okay, so this is nothing but the rigid body motion. This is nothing but the rigid body motion that we learned in fluid dynamics. For instance, the studies of tornadoes and all those kind of things that we learned in our basic elementary fluid mechanics class was basically the rigid body motion. And I'll tell you why this is known as a rigid body motion. Okay, so this is known as the rigid body motion. And before like me telling you what's basically why this is known as a rigid body motion, I would also like to show you how this pressure, so how this pressure essentially balances the centripetal, or basically the centrifugal force. Okay, so let's now see what basically is happening inside the two cylinders. Okay, so if I draw the cross section of the cylinder, the two cylinders basically look something like this. This is not concentric. All right, this more or less looks like a concentric cylinder. Let's shift this here. All right. Okay. So now, if I want to visualize what basically is happening inside this cylinder, so let's say we are looking in the r theta plane, which means that this basically is my r direction. This basically is my r direction, and this in the Cartesian coordinates will hence be the x and y direction. And now, if I randomly pick out a fluid element here, if I randomly pick out a fluid element here, okay, and then what I do is, so let's this be the fluid element, and I just zoom in this fluid element. Okay, if I just zoom in this fluid element, the fluid element would basically look something like this. Okay, so what we saw is that if we look on this surface, if we look on this surface, the pressure on this surface on the fluid element would be what? It would be P1, right? Let's say it's P1, where P1 is some value. And on the other surface, if we look at the pressure would be P2. And what we found out by applying the R momentum equation is that del P by del R is basically equal to what? It basically equal to rho times of R times omega squared. Okay. So this is the del P by del R expression that we got. Now, since this density is always, so the density is always greater than 0, that we know the density of a fluid can never be 0. The radius of so the radial direction can also never be 0, because radius starts from 0 to positive 0 to plus infinity. Hence, this is also greater than 0. And the angular velocity can be 0, but since it is omega squared, this term will also has to be greater than 0, which means that del P by del R is a positive quantity basically. This means, since del P by del R is a positive quantity, can you tell me what will be the signs of P? So can you just tell me, if del P by del R is a positive quantity, and if this is my radial direction, which of these would be true? Can you tell me, is P2 greater than P1 or P2 less than P1? Can you tell me from this one? Which would be true? Yeah,
P2 greater than P1.
exactly. P2 has to be greater than P1. The reason behind this is that since del P by del R is greater than 0, this means del P essentially has to be greater than 0, and del P is nothing but P2 minus P1, right? And since this is greater than 0, P2 has to be equal to P1, which means the net pressure force. So can you tell me what will be the direction of the net pressure force? Will it be in the plus R direction? I mean, will it be outward or it will be inward? Can you tell me?
Radially inwards.
Radially inward, yeah. So the net pressure force, is basically radially inward, which is obviously in towards the center of the cylinder. Okay, so this is the net pressure force. And since, so you know that since there has to be a balance, then the centrifugal force will basically act in the centrifugal force will basically act in the radially outward direction, and hence there would be a balance between these two forces, and that's why we get that rigid body motion that we saw. Okay, so this is the physics actually behind this. I hope this is clear. This is just a force balance, but to visualize how this force balance is taking place is something that we must understand. One more thing I would point out here is that if we draw the streamlines, okay, if we draw the streamlines of this, the streamlines would basically be something like this. So the streamlines of this flow would basically be something like this, where we know that at each and every point, if we draw the tangent to a streamline, it gives us the direction of the velocity. So we know that the tangent to a streamline would just be u theta, and u theta is nothing but what? It is just omega times r, which is just a scalar product of omega times r. So at this point, the u theta is omega times r. So at this point, of course, it will again be omega times r. So as you can see, the streamlines for this fluid would just be concentric circles. And at each point, u theta will be just the function of the angular velocity multiplied by this r, where r would vary basically in this zone. Okay, so you can now understand the streamlines would be just concentric circles. So now if I draw the streamline, so this is one set of streamline. So the other streamline basically be something like this. This would be the other set of streamlines, as you can see. So similarly, the third set of streamline would be something like this. This would be the third set of streamlines. And the direction, of course, depends on which sense omega is rotating. It can be either clockwise or counterclockwise, depending on the sense of the rotation of the two cylinders. But my point is not that. What I want to portray from this point is that whenever the streamlines are curved, this means there has to be a pressure gradient in the cross streamline direction. See, for instance, in the in the flow problem, for instance, if there is a quaid flow, you know that the streamlines are nearly parallel, and that's why there was no pressure gradient in the y direction, and we found out that del p by del y was basically equals to 0. However, if we see there is the streamlines are essentially, so if we see the flow is taking place in a curved plane, or if the flow is moving around the corner, there has to be a pressure gradient that is basically acting across the streamline. Okay, and this pressure gradient is actually what driving the flow, and this pressure gradient is actually what turning the flow around it. And and since, as we know, the momentum equation is just the balance between the forces, since the flow needs to maintain its trajectory in the theta direction there, so this force, which was basically due to the pressure gradient, should be balanced by the centrifugal force. That is essentially the dynamics of a circular motion of a, so this is basically essentially the dynamics of the rigid body motion, what we essentially learned in fluid mechanics course. So I hope this is clear. I hope this is clear. What essentially meant by rigid body motion by taking this special case. I would stop here for some time again. If you have any doubts on this, this is very important and you need to understand. First of all, why the streamlines, first of all, why there is a pressure gradient across the streamline whenever the streamlines move in a curved direction, or whenever there is a non-zero radius of curvature for a particular streamline, and the fact that why this is a rigid body rotation. So one thing is still left to answer, that why this is known as a so we now understood that there would be a balance of this pressure force and the centrifugal force, but we have not we have not still answered why this is a rigid body motion, and we will shortly do that. But before that, if you have any doubts, you can ask me. I'll stop here for 1 or 2 minutes and then we will begin. All right. So if you don't have any doubts, so now let's do one thing. So the velocity profile, okay, that we got for this case is u theta is basically omega r, okay, as you have rightly pointed out. So let's do one thing. So since we are in the since this is basically the r theta plane that we saw, where the theta direction would basically be something like this. So when, of course, r changes, the direction of theta coordinate also changes. So let's do one thing. Let us evaluate the viscous stress tau r theta in this case. So in cylindrical coordinate, the viscous stress is basically given by, so I'll just lay down the formula for viscous stress. This is just r times del r of u theta by r plus 1 by r times del ur by del theta. So if this is the expression for the viscous stress in the r theta plane, of course, for this chosen velocity profile, can you tell me what will be the value of tau r theta for this case? That is simple, right? Because we know u theta.
0.
Yeah, yeah, exactly. That is 0. For the sake of clarity, I would just show the viewers like why this is 0. So basically, you just need to see ur is anyway 0 because that is from our assumption. And you just need to evaluate this del r of u theta by r, this term. And from here, if you just evaluate u theta by r, it is just a constant omega, which means del r of u theta by r is just del r of omega. And since omega is constant, this is equal to 0, which means tau r theta is this, in this particular case, is 0. And that is typically the reason why this is known as a rigid body rotation, because there won't be any shear forces acting on the fluid element, as I have already said. This means whenever the fluid rotates with this omega r, the fluid elements would not suffer any shear stresses, and that's why the volume of the fluid element would remain intact. Okay, I mean, that's not the volume. The shape of the fluid element would remain intact. That's the more correct way of saying this statement. And that is why this is known as a rigid body rotation. Okay, and that is why this is known as a rigid body rotation, because the only way a fluid element can deform is either you apply a compressive force, which is not the case here, or there is a viscous stress that is being applied for on that fluid element. And since these two are absent, the fluid element would not deform when it undergoes this continuous rotation in with a velocity omega r. And that is why this motion is basically known as rigid body rotation. Okay, I hope this is clear. So I hope like this special case is clear, and this was something that I wish to say based on the previous problem. And see, you can also like have a hint why why this is a rigid body problem is that if we apply the momentum equation in the r direction, we saw that the viscous term essentially drops out. See, this term essentially became zero, right, by invoking all the assumption, which means and all which means that there won't be any shear stress if we take any arbitrary fluid element as the one that we saw here, Okay, so this is basically the idea of rigid body rotation. And this was something that I wished to say. Okay, all right. So can you tell me, I was just thinking here, can you tell me what the velocity field, so at any radial r, can you tell me what the velocity field would look like? So let's think about this. Let's think about how can we draw the velocity field. So since we know that, so what do we know? We know that u theta, u theta is, oops, u theta is basically omega r, okay? Which means ur is 0, that we already know, and uz is also 0. This is also known to us. So let's now try to draw the velocity field here, okay? We know, so we drew the streamlines. So we drew the streamlines here, but let's also try to draw the velocity field, and let's try to visualize. So at r equals to what? So let's say at r equals to a, u theta is just omega times a, and at r equals to b, u theta becomes omega times b. Okay, and since we know that, what do we know? Since we know, so I think a is the radius of the inner cylinder, right? Let's have a look. Okay, a is the radius of the inner cylinder. Since we know a is less than b, this means that u theta at a would obviously be less than u theta at b. And let's now try to draw this here. So if our cylinder is basically rotating in this direction, then the u theta at this point would be just omega times a, which would be something like this. Okay, I'm just drawing on this point. Okay, so the u theta would be omega times a, and we know this value, this is omega times a, and the u theta at this point would be what? It would be omega times b, and this would be larger because b is greater than a. It would be omega times b. So this would be the velocity field in the theta direction. Okay, this would be the velocity field in the theta direction. And remember, I'm just drawing on this radial line, meaning this radial line. Okay, so this would be the velocity field. So it will be something like this. All right. So if I shift my radial line to some other line, for instance, I want to draw on this line, let's say I want to draw on this line, then the velocity field would be something like this. So this would be omega times b, and this would be omega times a. All right, and the other velocities would be something like this, which should always be tangential to the streamlines, as we have already seen. So since the tangent to a streamline gives the direction of the velocity field, which the idea is indeed preserved here. Okay, so this is how the velocity field would look like, and of course you can see this is the rigid body rotation because this velocity field would just prevail around this theta direction without changing the shape of the fluid element. All right, guys. I hope this is clear. I hope this is clear to all. So again, I'll stop here for some time. I hope you got, so essentially you got how to draw the streamlines and the velocity profile here. Okay. So with this, I would again basically stop for 1 or 2 minutes, and then I'll begin with something new, as I think you didn't learn like I hope you didn't learn this in the courses so far, and hopefully we'll gain some insights from this. So this is typically known as scaling analysis and non-dimensionalization. Scaling analysis and non-dimensionalization. And of course, we will start from the very elementary concept, non-dimensionalization. Okay. But before this, I would stop here for some time. If you want to write notes on the previous analysis, you can, of course, write, or you can at least visualize by yourself and think about what I basically told. And then we will start off with this non-dimensionalization and scaling analysis. In the meantime, I'll just fill my jug and I'll come in 1 or 2 minutes. All right, guys. If you have any questions, you can let me know, and or else we will start off with something known as the scaling analysis in shortly. Okay. So if you don't have any questions, we will start off with something which is known as scaling analysis, and in particular, we will see something which is known as characteristic scales, and how the choice of this characteristic scale helps us in basically non-dimensionalizing a problem from its dimensional counterpart. And this is something that we will see subsequently. But let's first understand what basically are these characteristic scales. Okay. So for instance, I'd start off by writing something which is known as choices of scales. And let's see what essentially is this. So I will just pick up a very simple example that there is a flow. Okay. There is a flow of fluid. So let's say there is a flow of fluid through this parallel plate channel, as you have seen multiple times. Okay. And this channel obviously extends to the plus axial directions. Okay, so this channel basically extends to infinity. So if I take this to be my x direction, if I pick this to be my y direction, and of course if this is basically our center line, then at each axial location, if we are considering that the flow is hydrodynamically fully developed, then at each axial location we know that the velocity profile is basically parabolic. Okay, so this is something that we know and we saw multiple times. And here the velocities would be 0 because of the no slip condition. So what we can do is that, so we know that the velocity profile would be a parabolic profile, and the central end velocity for the corresponding velocity profile is a known quantity. Let's say it's u max. So the idea is that whenever we are going to solve a problem, which is basically this kind of problem, we can choose a defined scale for a velocity. Okay, and the defined scale, so what the idea is that we can choose, and we will see why do we choose these scales shortly. So we can choose a defined scale for the velocity field, let's say. And that defined scale is either known to us or it could be derived indirectly from the known quantities. Okay. So this means the idea is if we choose the correct, so let us just write, let UC be the characteristic scale for velocity. Okay, then we can choose UC to be either U max or U average. Okay, which means for this for this particular problem, I am choosing my characteristic velocity to be to be either the U max or U average, because so you can choose U max or U average, and that's completely up to you. But the idea of choosing this characteristic scale is that if I now consider a velocity field, let's say, if I now consider a velocity field, let's say U in the x direction, the idea is that the magnitude, so the idea is that the magnitude of U should be of the order of, so the magnitude of U should be of the order of this UC. Okay. This means that if I choose the velocities, so the idea is that U, which is basically the x direction velocity, and this means that it should be of the order of this U characteristics. Okay, this means that U can be anything, like, so the x direction velocity. So if we, so let's say for this problem, U max is, let's say, 20 meter per second, let's say. Okay, and so U average becomes U max by, so it's 2/3 of U max. So it is just 2/3 of 20. Okay, so this means that if I now choose the velocity scale, so if I now choose my characteristic velocity as either U max or U average, the velocity, the actual velocity field that we get, this should be close to these quantities. Okay, that is what the, so that's what the meaning of order, so that's what the meaning of order actually suggests. So it's not exactly equal to 20 or 2/3 of 20, but it's a ballpark figure between these two quantities. So that's the idea of choosing a characteristic scales. Okay, now the question is why you are doing this. So why you are doing this unnecessary business? That's something that that's the question that comes to our mind, right? And we will see this very shortly. So the idea of choosing a characteristic scale is that if we now choose a characteristic scale and then derive a non-dimensional quantity out of this characteristic scale, we essentially get a non-dimensional equation. For instance, if we non-dimensionalize the Navier-Stokes equation, as we will see either today or in the next class, we can remove all the dimensional quantities and we just end up getting a non-dimensional equation, which is thus where the quantity that of interest we get apart from the velocity field and the coordinates is the Reynolds number. So just by tuning the Reynolds number, we can get different velocity field, and that is the beauty of non-dimensionalization. So bear with me, this could be of little like difficult to you now, but as we move along, we will be very clear so as to what non-dimensionalization mean. Okay, so is this clear or not? So what is the choice? So how do we select these characteristic scales? Is this clear or not? Like I would stop here again for 1 or 2 minutes and basically allow you to digest like what I basically said. Okay. So did you get the idea of how do we choose a characteristic scales? So remember, it is, so the characteristic scales that we choose is actually a function of the physical picture. Okay, if I get a different problem, let's say if I get some different problem, which is not basically this problem, then the characteristic scale would change according to that problem, and it is up to us how do we choose that characteristic scale. Okay, so I hope this is clear. I hope this point is clear. So now let's look something else. Okay, based on these things. So we have seen how the characteristic scales of velocity look like. Let us now see length scales. Okay, so can you tell me, based on this physical picture only, if I now take that the channel height is, let's say, 2h, okay, and the channel length, let's say, is L. Okay, so I have given it two dimensions. The channel height is 2 times of h, or let's say it is, so 2 times of h is, let's say, some other number. Let's say what? Let's say g, which is equal to 2 times of h, where g is just a number equal to 2 times the height, where h is basically this. Okay, so my question is, what would you choose as the length scale? Okay, where we got two quantities now, it's g, which is basically this dimension, and the length of the pipe. So can you tell me what characteristic scale would you choose as your length scale? Will you,
G.
yeah, g, and why not L?
Because radial direction only variation is there, and
Exactly.
that if you check lengthwise, it will be not ordering to that scale.
Exactly. You have pointed out the exact statement that basically should be the essence of choosing a characteristic scale. So, as you have rightly pointed out, we will choose that scale on which the quantity of interest essentially varies. Okay. So, now the idea is that if we choose this L scale instead of choosing G or H as the characteristic scale, the thing is that the flow is already hydrodynamically fully developed. Okay. This means if I move along the x direction, there is no point where the velocity field would vary. Okay. So our point of interest is to capture the radial variations of the velocity field, and that's why we will choose the scale which is basically, so we will choose that scale which captures the physics of the problem. This is the essence of choosing the scales. Okay, so I'll write here, we will choose that scale that captures the physics. Okay, and that's why the characteristic length scale, we will denote it as LC, would be, so you can choose either G or you can choose H, that is up to you. But you cannot choose length as L. Okay, so LC you cannot choose as L. Okay, this is something that is important. Okay, so moving on, I hope you understood this nicely. So this is, so okay. So the first one is the velocity scale. Yeah, do you have any doubts?
No.
Oh, okay. Fine. So next, let's look into something more interesting. Can you tell me how stresses scale? Okay. So let's see scale for stresses. So before that, I would just pinpoint, or I would just give you a tip here. So if let's say a quantity x scales as a, okay, or this is something that we write. So if a quantity x scales as a, and if a quantity y scales as b, then can you tell me how does dy by dx scales as?
Y by A.
It's b by a, right? B by
Ah,
a.
sorry. I'm
Yeah,
sorry. B by A, sir.
b by a. Yeah, exactly. So in the same spirit, now let us see how do we so how do we essentially scale the viscous stresses? Okay. So in index notation, if so again, I'll, in the time being, like then and again, back and forth, I'll always bring the index notation because this is always like helpful to us. So in index notation, the viscous stress tau ij is basically written as mu times del Vi by del Xj plus del Vj by del Xi. And if you are not familiar with the index notation, let's say we write this in the xy coordinate system, then it will just end up be, so we'll just end up getting tau xy as mu times del, so this would be, so I would be x, so that's why it would become u, which is the x direction velocity, and j would be y, that's why it would become del u by del y plus del v by del x. Okay, so this is just the special case, and this is the general case where we write this in index form. Okay, so now let's see how does how does our viscous stresses scales as. Okay, so you can, so from this you can either write that this tau, so you can just write that this tau essentially scales as mu times some derivative of velocity by some derivative of length. Okay, let's say I write this length as, let's just write, okay, let's, for the time being, let's just write this to be u and this to be x, because the idea is that since there is a plus sign, this means the scaling of these terms should be equal to the scaling of this term. This means these two terms have equal dominance over this tau xy. I hope this you can understand this. Okay, because tau xy is written as a summation of these two terms. So I can just write that tau xy is roughly equal to mu times del u by del x. This is just to derive the scale of the viscous stress. Okay. Now you can just tell me, can you tell me if u scales as some uc, which is the characteristic velocity, and for the plain possible flow that we saw, uc is just u max or u average, and if let's say, okay, this is y basically, this is basically y. Okay, and and if y scales as basically equal to h, then as you can see, tau will scale as mu times del u by del y, which will basically scale as uc by lc, because h was basically our length scale lc. Okay, so this is known as, so this is basically the scale for viscous stresses. Okay, this is something that you need to know. Okay, so this is basically the scale for viscous stresses. All right, so far so good. Okay, so I hope this is clear how the stresses scale like. So let's just quickly recapitulate what we did. So we saw the scales of velocity, we saw what's the length scale is, we saw the scales for stresses. Okay, and now I hope this is clear. Now let's see two more things, and then we will like recapitulate what essentially we did, and we will get a clear idea of what, in what direction we are moving actually. So let's see one more thing, which is known as the time scale. Okay, all right, just 1 second, check this. Okay, so the choice of time scale is that, of course, in context to the fluid mechanics problem, is that we seek, so the idea is that we seek the time span over which there is over which there is a considerable change in velocity. So what does this mean? So as the line suggests, we will choose that time scale over which we see an appreciable change in the velocity field. Okay, so this means let's try to understand a most simplest case as what we can see. So let's say there is a bird. Okay, let's say there is a bird which is basically flapping its wings as it moves through the air. So there is this air that is surrounding the bird, and when the bird moves basically through this fluid, okay, it just flaps his wings, okay, so as to like hover, or so as to like cruise through the atmosphere. Okay, So for this problem, let's say we know what is the angular velocity, or let's say the frequency, or let's say the angular velocity at which the bird flaps its wings. Okay, so now if I want to solve this problem, if I want to solve this fluid mechanics problem, so what the fluid mechanics problem of this would be? So the most general, and the most obvious question is that if the bird flaps its wings with omega, how the air surrounding the bird would get disturbed? Or in other words, what would be the disturbance velocity profile when the bird moves, when the bird basically moves through this quiescent air? Okay, so then can you tell me what would you choose for this problem? So what would you choose at the time scale for this problem? Can you tell me what would be the time scale TC? So what would be TC? Do we have a definite time scale here, or do we need to derive the time scale, or do we see an obvious time scale of this problem?
1 by omega.
Exactly. So this is obvious, right? That is simply because the disturbance velocity is solely responsible. So, I mean, the disturbance velocity would only arise in the order of how the bird essentially flaps his wings, right? So if it flaps its wing faster, if it flaps faster, then the fluid will disturb more rigorously, or more, so the disturbance velocity would be more, like, so the frequency would be more basically. And if it flaps slower, the disturbance would propagate in a slower sense, which means that the considerable change in velocity is indirectly or directly related to the frequency at which the bird flaps its wings, and that's why the time scale would basically be omega inverse. Okay, but there are also certain instances where we do not have a defined time scale of the problem. So as I have said, this omega inverse is basically the defined time scale, because this is already known to us. Okay, however, in most of the cases we don't get a defined time scale. Okay, for instance, can you tell me what will be the time scale of this problem? Let's say we are not considering a fully developed flow, and let's say we are now considering a developing flow in a plane. So let's say we are now considering the developing region of that plane possible flow problem. In that case, we don't know, right? We don't know what's the time scale. So can you tell me how do you find the time scale here?
H by U max. H by UC.
Exactly. So that depends actually. So you have chosen so I understand what you said. So you have chosen the advection time scale, which is basically the length divided by UC. But there is also one more
Yes.
time scale, as I will show. And I would say that depends on a certain quantity, and essentially that depends on the Reynolds number basically. Okay, and I will exactly show you why is that case. But before this, let's wait for some time and just allow the viewers to, like, understand what we did so far, and then let's see what would be the time scale. Okay, we'll just wait for 1 or 2 minutes, and then we will see what will be the time scale associated with. All right, so let's do this. So let us see the time scale associated with basically the developing region. Let us see the time scale associated with this developing region of this plane possible flow problem. Okay, that is something that we will do. So there are two ways in which we can find the time scale of this problem. Okay, so let's write this is basically the time scale of the developing region. So the first scale, as you have said, is the advection time scale, as you have rightly pointed out. An advection time scale, so this is very simple. If we choose the advection time scale, it is generally known as TA, and this is nothing but the characteristic length LC divided by the characteristic velocity UC. And in this case, as we have said, it is just H by UC, and UC can either be U max or U average. Okay, but we can also choose a different time scale for our time, for representing the characteristic time. Okay, and just keep in mind that just because you choose a different time scale doesn't mean that your problem would basically be wrong. So if someone says what not if I do not choose the adjacent time scale and choose a different time scale, it's not wrong basically. So long as you capture the physics accurately. Of course, your governing equation would change accordingly, but the answer that you write, of course, will matter only to the fact that you choose the scale such that you capture the essence of the velocity field and basically the quantity of interest perfectly. That's the idea behind choosing scales. Okay. So let's say I choose a different scale, and this scale is basically known as the diffusion time scale. Okay. So this would basically be the advection time scale. To basically be the diffusion time scale. All right. So in order to find out what a diffusion time scale would be, I quickly write down the equation. I quickly write down the equation basically which governs the flow. Okay. So which is nothing but the x direction equation. So if I write down the x direction equation, it would be what? So the x direction equation would be del u by del t plus u times del u by del x plus v times del u by del y. And I just considered a planar flow. Then there would be this pressure gradient, which would be del p by del x plus mu times. It is just del square u by del x squared plus del squared u by del y squared. Okay. So now, can you tell me which two terms do we need to compare? Which two terms basically we need to compare? Okay. If we want to find out, if we basically want to find out the diffusion time scale, can you tell me which two terms do we need to do the order of magnitude analysis? Think about it. So so what do we want? We want the diffusion time scale, right? So the name suggests that now we need to do the order of magnitude analysis of the state of this term with the diffusion term, right? Which is basically this term. So let's do this. Okay. Let's do this. So what we were saying is that del u by del t, if we say its scale says this term, and I just consider without the loss of generality just this term del square u by del y square, which means del u by del t would inevitably scale as mu times del square u by del y square. So now let's do this. So del u by del t. So what is the scaling of this del u by del t? Can you tell me? So it's just uc by td, where td is now the diffusion time scale because I am equating this term with a diffusion term. Okay, and this should be the order of mu times. So can you tell me what would be the order of magnitude of this term? Can you tell me now?
UC by L square.
Yes, exactly. So this would be UC by LC squared. Yes. So by now, I think you guys understood what basically is the order of magnitude of derivatives. Okay. So if you simplify, this becomes, so what does it become? This becomes, so TD is basically LC square by mu. And this is known as, this is known as the diffusion time scale. Okay. So the backdrop is basically the fact that if we are not given an inherent time scale of the problem, we can either choose the advection time scale or the diffusion time scale depending on the physics of the problem. So for instance, if I want to study the flow of honey that is flowing through a channel, what time scale would you choose? Would you choose the advection time scale and or the diffusion time scale?
Diffusion times.
Diffusion time scale, right? Because the Reynolds, so honey is basically a very viscous fluid, which means the Reynolds number typically of such problems uh, is basically very small, and that's why we will choose the diffusion time scale in order to accurately capture the essence of the problem. For instance, can you quickly tell me? We saw that the advection time scale just by mouth we say that it is LC by UC. But can you tell me from this equation which term do we need to compare in order to get the advection time scale now? Can you tell me? So you said the answer
Du
is
by dt and
yes.
yeah, du by
You
dt with that grade dot u.
this term, right?
Yeah, this time.
Exactly. So that is indeed correct. And as you can see, if we just compare these terms, so what we will get is del U by del T essentially scales as UC by T advection, and this would basically scale as UC squared. And I'm considering that X and Y basically bears the same length scale, which may not be the case, but I'm just considering the fact that they bear the same scale, and then this would just become LC, which means you can very easily say that TA would basically be LC by UC, which is the advection time scale. All right, guys. So I think this is clear to you. Okay, how to choose the time scale now. One final thing about the scales. Okay, and that is very interesting. But just before that, can you just tell me what is the ratio of T diffusion by T advection? Can you tell me? So let's do this. T diffusion is LC squared by mu, and T advection is what? It is LC by UC. So can you tell me what is this ratio? Oops, I think I missed something.
You
Okay.
see LC by me.
Yeah, it's yes. Sorry, I just missed something. So the diffusion time scale is what? That is mu. Oops. It will be mu. So did I miss something? So diffusion time scale is okay. I just missed the thing. Okay. So there should be a row here, right? Because this row should be
Yes.
multiplied here, right? Which means there would be a row here, which means there would be, so this row would be basically there, which means this would be LC squared by nu and not LC squared by mu. Did you understand what I said?
Yes.
Yes, exactly. So this diffusion time scale is basically LC squared by nu, since nu is basically what? So nu is what? It is mu by rho. Okay. All right. So based on this, can you now tell me what is the ratio of TD by TA?
It is Reynolds number.
Exactly. Exactly. Just one second. So if I now choose, if I now, okay. So the idea is if I just simplify this term, this becomes what? This becomes LC times UC by nu, and this becomes LC UC. Nu is basically mu by rho. So this becomes rho LC UC by mu. So what did we get is that, pardon me, I just said the statement a bit wrongly, which is not the case. I'll just clarify this why I said that wrongly. So the idea is that the ratio of this diffusion to advection time scale is nothing but the Reynolds number. Okay. So I said that if the Reynolds number is high, we will choose the advection time scale. But that is so let's just see this systematically. Okay. So if Reynolds number is very much high, what does this mean? This means that TD by TA is very much greater than 1, which means TD, the diffusion time scale, would be very much greater than the advection time scale. So the idea is that if we have a scenario where the Reynolds number is very high, this means that the diffusion time scale would be very much larger than the advection time scale, and we choose the lesser time scale because the change would occur always in the lesser time scale. Okay, this means that if Reynolds number is high, we will always choose the advection term, okay, as our time scale. In the same spirit, if Reynolds number is very much less, we will choose as TD to be our time scale of the problem. See, the physics is that if Reynolds number is very much high, what we saw is that the diffusion time scale would be very much larger, which means let's say the diffusion time scale is let's say around 60 seconds, while the advection time scale is let's say 2 seconds. So it's natural that if we want to capture the physics very accurately, we will choose the smaller time scale, right? Because what if so that's very obvious, right? What if there is an appreciable change in 10 seconds? then the diffusion time scale would not capture this, right? But because the diffusion time scale is basically 50 seconds, right? So that's why we will always choose the smaller time scale that is associated with it. So that's what I choose. That's what I will tell. The rule of thumb. So the rule of thumb is that always choose the smaller time scale. That's the idea. So is this clear or not? Like, I hope this is clear. Because again, the very definition of choosing a time scale is that we want to mimic or we want to capture. So the idea is that we want to capture how the velocity changes within that time scale. So that's why we will choose the smaller time scale, basically to be in the safer side, so that we capture the essence in the so that we capture the basic variations in the velocity field that we see. Okay, so that's the idea. So in simple words, the idea is that always choose the smaller time scale. Okay. So one final thing before we call it a day, and can you guess what we are left? So we saw the scales of velocity, we saw the scales of length, we saw the scales of stresses, we saw the scales of time. Can you like guess what else it is
Pressure.
basic? Yes, exactly. So we are finally left with scaling of pressure, and that is the most interesting bit of the scaling analysis. Okay, and this is known as the scaling of pressure. But before this, I would wait here for 1 or 2 minutes. If you have any doubts, you can obviously like raise here. All right. So if not, let's see how the pressure term scale says. And in order to nicely understand how to choose the scale of pressure, let's write the Navier-Stokes equation in a vector form. Okay. So if I write it in the vector form, so instead of writing those whole lot of terms like del u, del x, del v, del y. Let's better write it in the vector form in order to have a concise like understanding of it. So in vector form, it would be just del u bar by del t, where u bar is now the velocity field, and it is u bar times grad of what u, and this is 1 upon rho times grad of p plus nu times del square u. I hope this is very much clear. How did I get this vector form? This is so the vector form, the different forms in different coordinate systems, and the index notation. This should be like so you need to go through this back and forth so that you have a clear understanding of all those forms in this course. Okay, because we will use this in many a times in several ways whenever necessary. All right. Now let's tell me I have so what I put forward is that I have a defined time scale TC of my problem. I have a defined length scale LC of my problem. And yeah, and what do we need? And my idea is that if I know these two things, what would my characteristic scale of pressure be? So this is something that we seek to find out. So the idea is what would be the scale for pressure. All right. So before finding the scale for pressure, what we will do is we will first list down the scales that is associated with these terms. Okay, this term and this term. So can you quickly tell me what would be the order of magnitude of del u bar by del t? Can you tell me this? What would be the order of magnitude of this term based on these two scales? Of course, I tell you that my velocity scales as you see.
L square by L square.
Yeah, I so let's not write it in L square and T. Let's just write it as UC by TC. I hope you can understand this. Okay. So this is fine, right? Of course, you can choose UC as LC by TC or something like that, but let's now keep it as UC. I hope you can understand this. We will not bother about what UC is. You can choose UC depending on the physics of the problem, but let's now keep it as UC. Okay. Based on this, can you now tell me what would be the scale for this term in terms of these three quantities? u dot grad, sorry, this is
UC square by LC.
exactly. So this term would scale as UC squared by LC. All right. Similarly, what would be the scale of this term?
UC UC by L square.
And there would be nu, right? This would be UC by L
Yeah,
squared.
yeah,
Yes.
yeah.
All right. And now, if I want to find out the scale of this term, 1 by rho grad P, this would be just, so can you tell me what would be? This would be PC times rho by LC. I hope you can understand that.
Yes.
Okay. All right. So we are done with the order of magnitude of different terms that arises in this Navier-Stokes equation. Okay. All right. So here lies the ambiguity. So I say this as an ambiguity because we now have two options. Okay. So I will write the first option. The first option is that my pressure term can scale as the viscous term. Which means what? Which means that the scale of this term is equal to the scale of this term. And if we do that, what do we get? We get, so the pressure term is what? It is minus grad P times 1 by rho, and this scales as what? It scales as nu times del square U. And we found out that this is nothing but PC by rho LC. We will disregard the minus signs because we are only interested in ballpark figures. So this would scale at PC by rho LC, and this would basically scale as mu UC by LC squared. So from this, okay, I hope, please see the algebra correctly. I hope this is correct. Okay, so from this, if I just simplify, what do we get? So this is LC squared, by the way. So this is just be LC. So I think from this, if we find out PC would basically come out to be mu times UC rho by LC, if my math is correct, and this would become PC as mu UC by LC. All right. So what we found out is that if I equate the scales of pressure with the viscous term, if my pressure term scales as viscous term, what I get is that PC is nothing but mu EC by LC, and this is known as viscous scale for pressure. All right. So what is the second option then? If my pressure scales can scale as a viscous term, what is the second option that with which my pressure term can scale as? It can either scale as this term, or it can either scale as this advection or any of these two terms. Okay. So now the idea is that if my pressure now scales as this advection terms, let's see what do we get. Okay, so this is the second option, that if pressure scales as, so if the pressure term scales as the advection term, this means what? This means that minus 1 by rho grad of pressure, this should scale as, so it can either scale as this or it can either scale as this. However, you can always link PC with LC and UC based on the fact that PC is just LC by UC. So these two terms will inevitably or will finally be the same term that we essentially seek for. So that's why if we can write TC in terms of UC and LC, I just choose this term only, which means this should scale as UC squared by LC. Okay, just let's not write this step here. So this is just this term, it is just U dot grad U. And if I write the scales here, it would be what? It would be PC by rho times LC. This would scale as we have said, it would be UC squared by LC, which means, what? Let's see what we get. So this LC and this LC will cancel out. So this PC would be rho times UC squared, if I am not wrong. So I hope my algebra is clear. So this PC would now be rho times UC squared. Okay. So this scale for pressure is known as, if that is known as the diffusion scale, this scale is known as advection scale for pressure. So now again, which scale to choose? So can you tell me what scale do we need to choose? Or if we are left in this scenario, or if we are left in this crisis scenario, which scale of pressure do we choose? And depending on what?
Based on whether viscous effects is dominant or
Exactly. Or
low
based on,
effects.
yeah, exactly. But what number does that signify?
Reynolds number.
Exactly. So that's exactly the whole point. Okay. So the way in which pressure would scale would be dependent on the Reynolds number. Okay. So the rule of thumb is that, again, I would say the rule of thumb is that if Reynolds number is very much less than 1, okay, this means viscosity dominates. This means viscosity dominates, and this means that pressure. See, this is very simple, right? See, if Reynolds number is very much greater than 1, which means that this term would basically dominate over this term. Okay, that means the only way that the pressure could like balance is by balancing with the viscous term. And that's why the obvious scale that the pressure would take is the viscous time scale, right? I hope this is clear to you. And this is pretty much simple, right? It's just that which term dominates over what, and this eventually gives us the scale for pressure. So PC would be, so if Reynolds number is very much less than 1, this means PC would be the viscous scale, and this is nothing but mu UC by LC. Okay. This is mu UC by LC. And on the other hand, if Reynolds number is very much greater than 1, as we have said, this means that the only way, see, the only way, if Reynolds number is very much greater than 1, this means that we know the inertia dominates. So the only way the pressure can balance this inertia is that these two terms should be of the same order of magnitude. And that's why PC must scales as, I mean, the pressure term must scales as the advection term. And then our scale for pressure would be, then our scale for pressure would be rho times UC squared, which is nothing but the advection time scale of pressure. Sorry, advection scale for pressure. Advection scale for pressure. So with this, with this, I finish the scaling analysis. Now, still there would be a question in your mind that why did we do this? Okay, we could have just solved the problem, that is solve the like flow problems by using the characters, I mean by using the given properties like mu and rho and all those things. So in the next class, we will have a clear idea so as to why we did this scaling analysis, and the next step of this scaling analysis is basically non-dimensionalization. So the idea is that we will define certain non-dimensional quantities which is based on, so we will define something which is the non-dimensional velocity, the non-dimensional time, the non-dimensional pressure, and the non-dimensional quantities would be the dimensional quantities divided by the characteristic quantity. For instance, the non-dimensional velocity, we will write it as u bar. This would be the dimensional velocity divided by the characteristic velocity. And this is a way of defining non-dimensional quantities, and that's why we define these scales in this manner. Okay, so this is the idea behind the choosing the scales. And I hope so in the next session we will solve a problem. Of course, today we didn't solve much of a problem, but in next session we'll solve a problem, and this is typically, and we will see that this is typically the reason why we do scaling analysis while we basically solve that problem. Okay, so I hope this is clear. So I
Yes.
hope okay. I hope this point is clear. So if you have any doubts, so we will stop here today. Uh, so I think we are done with this today's session. So if you have doubts, I'll wait. Obviously, wait for like 1 or 2 minutes. If you have doubts, you can, of course, clarify. And in the next session, we will basically start over from this from this part, and then we will see like how basically do we use this scaling analysis, and I think that would be much of a more fruitful session. But yeah, this idea needs to be developed, and that's why like I started very slowly with the scaling analysis and developed the certain reasoning behind choosing these characteristic skills. Okay, so if you have any doubt, you can ask, or else we will meet next week. And the next week will be the usual time, that is from 3 to 5 in Saturday, on Saturdays. uh, I mean the usual time slot that we have. And yeah, so if you have any doubts, you can point it out. If you don't, like, I will stop the session now, and we will meet next week.
No doubts.
Okay, thank you for joining this session. I will end the session now. Thank you very much.
Thank you.
Yeah, thank you.